Hansen. This is Ben Spatafora and Eric Burns, and we are the MET portion of the Formula SAE team.
So as far as Formula SAE, it's a competition in which schools and teams must engineer, design, calculate, and manufacture an open-wheeled race car to compete in a series of events. We compete against about 119 other schools, 120 in total, and come Monday of next week, we're starting to make our road trip out to Michigan in order to start the process. As far as the team goes, there's 3 of us METs and about 9 MEs. We use the MTL, which is the MET's home base, to do machining when Crosby Lab is full, and not to mention our tools are a little bit up to spec more, so we can hold tolerances tighter. Crosby Lab is the home base for the car, though. That's where the team meets, where we store everything, and where we make all the good things happen. Here we have the team, doing what we do best.
Alright, so the competition has different guidelines, and there are both static and dynamic events. Some of the dynamic events consist of things such as acceleration, autocross, a skid pad to see how many G's you can pull in the corner, endurance, and efficiency. And then the static events are things such as your presentation on the car, tech inspection. It has to pass a series of tests and inspections in order so that you can race it, so that's a pass-fail. Then there's also things such as a cost analysis where they analyze every single thing that's manufactured and bought on the car. So the price of the car, and then they also analyze the design of the car. And you score after that. Last year we scored 187 points and got 86th place out of 120 schools. This year we're planning on doing significantly better than that. An overview of the car. It's made out of 40-130 chromoly frame. The chassis is 65 inches long and weighs about 55 pounds, or 45. Yep. So for powertrain, it has a 2009 Aprilia RXV 550 dirt bike engine in it. It has about 65 horsepower. We're going to have a recluse auto clutch in it, which is going to do automatic shifting, kind of. And then we have a Drexler rear differential, which is the lightest rear differential in the world, weighing about 7 pounds. It's a limited slip with torque vectoring. And then we also have, for suspension, we have push rod configuration with Öhlins, shocks, custom uprights.
So as far as the team goes, each team member is more or less assigned a specific task to do, a specific part of the car to keep a hold of. And I was put on the cooling system, helping with engine calibration team. As far as competition goes, last year the car was running hot, overheated, just more or less did not run all that great. Not to mention, in the design report, you're supposed to have calculations to back up everything, such as your cooling system size. We did not have that either. So this year, I was in charge of that. Due to time constraints, I ended up not actually fully completing all the calculations. But we initially started to size up fans to get more CFM through the radiator to cool the car more. Not to mention coolant hose routing and the radiuses that it needs to get significant water flow through the cooling system. And this year we tuned the engine correctly. Last year it was not running so great, and the poor tune added to the hot engine temps. So a lot of time was spent on the dyno figuring that out. We stayed with the stock fans, and this year we added a circuit in to automatically kick them on over a given temperature, as opposed to last year, which we had one switch, and when you're racing, you're not going to say like, oh, I'm sitting here at the starting line, I better hit my fans on.
So personally, I designed the braking system for the car. Some of the issues were that last year there were no calculations to back up the braking system, which is part of the design report that you include for competition. So they deducted points from our score for that. And also last year with our different rear differential, we had one brake in the rear, one disc brake. And with the limited slip, we needed outboard brakes because one of the requirements is that you have to lock up all 4 tires of the car. So what I did is I created created math pad documents to design and specify the correct brake size for the car, and I used calculations including coefficient of friction, center of gravity of the car, weight transfer, weight of the car, to size the correct brake pads and rotors. And another thing that I helped design was the pedal box on the car. The old one was too heavy and it didn't have a clutch pedal. We had a hand clutch on the car. We decided that it would be more adequate and more marketable if we had a pedal clutch, much more like a typical car would, instead of a motorcycle. So we wanted a pedal box with a pedal clutch, and one of the specifications is also that the pedal box has to withstand 500 pounds of braking force. So we had to design it so that was like that. We made it on the water jet with some milling to create it, and we manufactured it to be as light as possible.
As stated earlier, one of the major problems with the engine last year was that it wasn't tuned properly. We had a really hard time starting, and then once it was running, it would run really hot. So I worked with the MEs to do the engine calibration this year. One of the first things we needed to do was verify that all the equipment we had was adequate, which involved sizing the fuel injectors and the pump and the filtration to make sure that everything was adequate for what we were trying to get out of the engine. Once we verified everything, we moved on to actually calibrating, which requires rewriting the fuel maps and the ignition maps to get the power output that we wanted and the right stoichiometric ratios. Once we got to putting it in the car, we discovered that there were a few things that still didn't fit right within some of the rules, so we had to redesign our plenum, which required us to rewrite our maps a little bit, and the exhaust had to be moved, which, once again, made us had to rewrite a little bit. The other thing I worked on this year was a pneumatic shifter that actually didn't make it on the car this year, but might make it on in future years. This was brought up because our car is extremely small. It's really hard to get a shifter in there, and this is a nice way to just move everything up onto the steering wheel so that you don't have to take your hands off to do anything. This uses two solenoids and has a paintball tank for your pressure. Uses a 1-inch throw, 3/4-inch cylinder set in the middle, so you get a 1/2-inch throw in each direction. And one of the things that we needed to calculate to make the system work was the coefficient of flow, or CD, which is basically like the resistance in the system for how fast you want it to react. Based on the information that I chose, it told me that I needed a CD of 0.09 roughly, and then so when I was sizing valves, I had to look for something bigger than that, and I chose a 0.12 valve, so it shifts like lightning basically.
So, in conclusion, I can say that as far as the project goes, we utilized the vast majority of all of our MET classes, be it circuits, machining, public speaking as far as that goes even. And we applied all the knowledge we've learned in the last few years to design, calculate, more or less figure out what it takes to engineer something and pull through in the manufacturing front. And work with a team of diverse skills. Everyone brought something to the table, and we used all of it. Any questions?